So the uniform distribution is kind of like what it sounds like. Uniform means the same, right? So with a uniform distribution, you have a continuous interval. So you can kind of think about it like it's on a number line. So you have the same probability for everything that's going to happen on that interval. You know, all of the distributions we looked at in the last chapter were discrete distributions. Remember how our variables were things like 0, 1, 2, 3, and we didn't look at the numbers in between those. Well, this chapter talks more about continuous distributions. So things like if I wanted to look at my weight over a 1-year period, well, it's going to go up and down, but it's, you know, I may weigh 500 pounds on one day. I don't weigh that much, but maybe I do one day, and then the next day I weigh 499.257 pounds, and then the next day I weigh 501 pounds. So I can be any value really imaginable. So if you think about that on a number line, and let's do something more realistic. Maybe I want to know how much weight that I've lost per month. If I'm trying to, let's say I'm trying to diet, I'm exercising every day, and I know that I'm going to lose between 2 and 5 pounds a month. All right. Well, if you think about that on a number line, then I can lose any value between 2 and 5. I don't have to just lose 3 pounds, right? I could lose 3.125 pounds. So values like that, that's going to be when we look at values like that, that's more of a continuous value because it can be any decimal in between in a certain range, maybe from 2 to 5. If you think about it like you would graph it, maybe if you were in college algebra, you know, it'd be any value in this interval, okay? And with uniform probability distributions, the probability is the same for every value inside of that interval. All right. A couple of formulas that you may need. The mean of a uniform distribution, it's really easy to find, probably one of the easier values. You just take, like our interval, you consider that first value to be A and that second value to be B in the interval. So the mean is just A plus B divided by 2. So you take the lower interval value plus the upper interval value, add them together and divide by 2. Now the mean, just take my word for it, it looks a little strange, especially if you're a math person. You always want to know how to come up with every formula. This one is a little tough to explain, and the reason why it's a little tough to explain is because you divide by the square root of 12. Okay? Deriving this formula, you do come up with that, but it's a little more complex than we want to do in this class to derive that. So you just have to kind of take my word for it. When finding the standard deviation, because that's what that symbol is, that's the lowercase sigma, find the standard deviation of a uniform distribution, you say B minus A divided by the square root of 12. So on this example that I have up here, if I wanted to find the mean, it will be 5 plus 2 divided by 2. All right, so that would be 7 divided by 2, or 3.5. If I wanted to find the standard deviation, the population standard deviation. That would be B minus A divided by the square root of 12. So that would be 3 divided by the square root of 12. And so I'd want to do that in a calculator. All right, and I'd probably round this to 3 decimal places. Usually the rule is one more than the original set of data, but really you just look at the directions and see. So that would be 0.866, about 0.866. And then of course if I wanted the variance, what would I do? I would take that answer and square it. Because remember, the variance is the standard deviation squared. All right, let's look at the example in the PowerPoint, and then we're going to move on. The example in the PowerPoint says the fire department records how long it takes each of its trucks to reach the scene of a fire. Suppose that distribution of arrival times is uniform, with the minimum time being 2 minutes and the maximum time being 15 minutes. Okay, so we're looking on the interval from 2 to 15 minutes. And by it saying that it's uniform, that means the probability of the fire truck arriving is going to be the same for every fire truck leaving. That would be a pretty important statistic if you think about it. Because if you want to know on average how many minutes it's going to take a fire truck to arrive to where it's going, I mean that could be the difference between life and death, and you definitely want to get that down as far as possible. It says let X be equal to the amount of time it takes the fire truck to arrive at the scene of a fire after being called. All right. So what is the probability that the truck will reach a fire scene within 5 to 10 minutes? All right. So for the uniform distribution, if we want to know the probability, the height of this, I guess you could, the way that uniform distributions could be drawn are like rectangles, because it's all this stuff right here, and the height would be the probability. And the way that you get the height of that line, and the scale isn't that great, but the way that you get the height of that line is you say 1 over B minus A. So 1 over 15 minus 2. What's that going to be? 1 over 13. So what that means is there is a 1/13th chance that the fire truck will arrive anytime between 2 and 15 minutes. It's the same probability the entire time. Okay? Now, there's a couple of ways to work these problems, and I don't always write down the height when I'm working these problems because I kind of use a little bit of common sense when I'm working these problems, and I'll show you what I'm talking about. What is the distance between 2 and 15? We just figured that out, didn't we? The distance between 2 and 15 is 13 units, like from here to here. That's 13 units. We want to know the probability that a truck will reach a fire scene within 5 to 10 minutes. So between 5 and 10 minutes, so I'd have maybe 5 about right here, and I'd have 10 probably about right here, maybe a little further over. But how many units are between 5 and 10? 5, right? 10 minus 5 is 5. So if I want to know the probability, it's simply going to be part over total. The part that I'm looking at, the distance between 5 and 10 minutes, over the total amount of time that I'm looking at, between 2 and 15 minutes. So the easiest way to work this problem is to simply say the probability of x, and that would be that it's going to arrive between 5 and 10, is equal to part over total. That's the easiest way to work the problem. And that's using a little bit more math sense than it is, I would say, mathematical theorem or mathematical formula. If you're the kind where you want to use a formula every time, and that's fine, what you need to do is you need to write the height of the curve or the height of the line, because that's going to be the probability. So that would be 1 over 13. And you would say that times the number of units between 5 and 10, which was 5. So 1/13 times 5 is 5 over 13. You get the same answer either way. I like to look at it as part over total because that makes the most sense in my mind. However, most math teachers, if this was just a pure math statistics class, this is for non-math majors or people that just want an elective. All right? So I'm just trying to give you other options, not to have to do it strictly by the math theorem or the math formula. Okay? So it's really just part over total. That's all it is, part over total. The part that you're looking at, the distance of the part you're looking at, over the total distance between the first and last value on the interval. All right, so not too bad. What about the mean? A plus B divided by 2. So, or B plus A divided by 2. It doesn't matter. So that's going to be what? 17 divided by 2, or 8.5. That's 8.5 minutes. And then lastly, what about the standard deviation? That's B minus A divided by the square root of 12. So B is 15 minus A, 2, divided by the square root of 12. So that's 13 divided by the square root of 12. Or if you do that in a calculator, you'll get about 3.753 minutes. So uniform distribution is pretty easy because the probability is the same for every value in the interval. And what did the picture look like if I graph it? It looks like a rectangle. Because the probability at any of these places, the probability at all of these places is the same. Probability for any minute in between 2 and 15, or any time in between 2 and 15 minutes on this problem, the probability is always 1 over 13. All right, let's move on to the next section, the normal distribution. Now, we've already looked a little at normal distributions. I've told you what it means for something to be normal. We went over the empirical rule. If you think back to the empirical rule, where with the empirical rule, remember the 1 sigma rule was that 68% of all data will lie within 1 standard deviation of the mean. And the 2 sigma rule was what? How much? 95% will lie within 2 standard deviations excuse me, of the mean. And the 3 sigma rule was that 99.7% of all the data items will lie within 3 standard deviations of the mean. And when we were looking at that, remember we were looking at the bell-shaped curve. The bell-shaped curve. And the bell-shaped curve, we use that for normal distributions. All right. Now the area under the bell-shaped curve, if this was on the X and Y axis, and I could figure out a way to find this area, which you can do, but you have to use calculus to do it. So, but we don't need calculus for this class. So just take my word for it. The area under this curve is 1 unit, 1.0. All right. Now, a lot of what we're going to do in here is going to depend on the area under this curve. A lot of what we're going to do in here going forward. And so, it's not, we're not going to get 1.0 every time, because we're just going to be looking at parts of the area under the curve, not just the entire area under the curve. Your book says that a normal distribution, originally called the Gaussian distribution, was named after Carl Gauss, who published a work in 1833 describing the mathematical definition of the distribution. Normal distributions are bell-shaped, but the bells come in various shapes and sizes. Since all normal distributions are symmetric, the mean, mode, and median are all equal. So with a bell-shaped curve with a normal distribution, the mean, mode, and median are all equal. And you may wonder, how could that happen? Well, the way that we have to use this curve, if we're not given values that are standardized, which I'll show you how to do that, then we have to use a formula to change them over into z-scores. Okay? We've done a little bit with z-scores, not a lot. We did very, very little. But we'll be using a lot of z-scores with our normal curve. All right. So let me show you, and again, this is going back to the empirical rule and what we already know, but let me show you a picture of the bell-shaped curve, a little bit better than the one that I've drawn, with standard deviations on or around the bell-shaped curve. So you can see here, make it a little bit larger. This is the 1 sigma rule, right, that we went over. And so you can see that if you find the area under the curve, all right, if you find the area under the curve that is 1 standard deviation above or below the mean, or the z value 0, then you can see that the area is 0.6826. Okay, so that's about 68%. That's where that comes from. Now, what did we say about the 2 sigma rule? Do you remember that? 95%. So if I looked at a picture at I say an exact area, but a real close to the actual area. I mean, it's hard to write an exact area because these decimals are not terminating. They do keep going on and on forever. But look at the 2 sigma rule here. This is what the picture would look like. And you can see within 2 standard deviations of the mean, or of z equals 0, we have 0.9544. That's about 95%. All right, and then within 3 standard deviations of the mean, and this is of course the last one. Remember, it was like 99.7%. So here's what the 3 standard deviations would look like. You see 0.9974. Now you do have some area still out here and over here, and everything here is very symmetric. What does that mean? That means if I divide any of these bell curves in half, if the area under the curve, if the entire curve is 1, so like, let me go up here, this would probably be better. If the area under the curve is 1, if I divide it into halves, then how much area do you think is to the left, and how much area do you think is to the right? If you divide 1 into half, 1/2, that will be 0.5 to the left and 0.5 to the right, right? If it's symmetric, if it's the same on both sides. Okay. Now we are going to use tables mostly when finding these values. And let me show you why we're going to use tables. We have a normal probability density function. And if I started trying to get you to find these values using the normal probability density function, you would probably be turned off very fast from this and say there's no way that I can learn how to do this, and maybe even consider dropping, because the function is a little, and it's kind of blurry because it was kind of small, but you can see the function is, it's kind of intimidating. All right, because, and I know you can't really see this very good, but that's negative x minus mu squared over 2 to the sigma squared, and that's the power of e. And then you have this in front, 1 over sigma times the square root of 2 pi. I mean, where does that even come from? Well, it's all the math that goes behind this in finding the values that we do. Okay? But we have tables that we're going to use to help us find all those values. We're not going to have to use that function to find the values. All right. So sometimes histograms can have normal distributions. There are a few examples in your PowerPoint. And here's the couple of examples here. I mean, these aren't exactly bell-shaped. Sometimes we may be skewed one way or the other. I guess this one right here is probably the one that will be the most closely bell-shaped if you just went around. I mean, that's not exactly like a bell, but a lot of times when we're dealing with things like weight and height and different things with population, we start actually crunching the numbers. We do have normal distributions. Now, the larger the size, you can see these sample sizes are pretty small, n equals 25. The larger the size that you look at, then the closer, or usually the closer that your data would look like a bell-shaped curve if you were to try to draw a bell around the data. So here's an example. Those two were when n was equal to 25. Well, here's an example of when n is equal to 200. So you can see that looks a little more bell-shaped. I mean, here it's kind of going down a little bit, but you know, if I drew a line and tried to touch best I could all of those, I mean, that would look a little closer to being a bell. And as that number increases and increases, then the normal distribution would be a special type of normal distribution called a standard normal distribution. Because as n increases, your values will make a bell shape, or you know, all the data items under the curve will make a bell shape if you graph it. Okay. So that's what a normal distribution is. And as your sample sizes get larger and larger, your data will approach being a standard normal distribution. Okay? And that's where we're moving to next. We're going to look at the standard normal distribution. All right? And so the standard normal distribution will always have a mean equal to 0 and a standard deviation equal to 1. That's a very important property of the standard normal distribution. All right, so if the mean is equal to 0 and the standard deviation is equal to 1, that simplifies things a lot. All right, and we can find areas under the curve, under our bell-shaped curve, very easily. So we're going to look at a problem, and this is in your PowerPoint. I want to explain how they get the answer and where they get the answer from. To do this, we're going to need the tables A. I think it's either A and B or B and C. Let me grab one of your formula sheets. So you need to look at the formula sheets that I've given you, the ones that I told you that you'd probably want to use on every test. And so all right, so let's see if we can figure out some of these areas. Now, normally what we're going to have to do to standardize a value, a variable, we're going to have to use the z-score formula. Remember, it was x minus mu over sigma. So that's if we don't have a standard normal distribution and we want to change it over and standardize the value. Because, okay, if we already have a standard normal distribution and I plug in a 0 right here, and I plug in a 1 down here, then z is just going to be equal to whatever x value I'm looking at, because the top would be x and the bottom would be 1, and x divided by 1 is just x. Normally, if we're doing real world problems, normally we don't have a standard normal distribution to start with, and we have to convert them over. But to start out with, we're just going to look at the standard normal distribution and assume that the mean is equal to 0 and the standard deviation is equal to 1, just so we can figure out how to find some areas under the curve. All right, the first example, and this one is also in your PowerPoint, it says compute the probability that a standard normal random variable is less than 1.27. All right, so I'm going to show you, I'm going to draw a picture of what we're actually trying to find. And then we're going to use the tables to find the value. Now, some of the more advanced calculators, there is a way to punch this in a calculator, but it's a lot easier just to look at the table, I promise you, if you understand how to use the table. All right, so here's what we're actually trying to find. Let's say that I had, well, let me just draw the bell-shaped curve. It's kind of hard without an x and y axis, but let's say that I had the good old standard normal curve here, standard normal distribution. Right here in the middle, we know that we have 0. All right, it's z equals 0. In this case, with the standard normal distribution, it's x equals 0. All right, now if we want to look at 1.27, then really what we're doing is we're looking 1.27 standard deviations above the mean. Because remember, if it's a standard normal distribution and that's 0 and that's 1, your z-score is just equal to whatever x value we're looking at, and the x value is the variable. So where would that be? Well, if I had to guess, and all this is just guesstimation drawing, you know, one standard deviation is, you know, probably about this far. So 1.27 would probably be just a little bit more. So I'm going to guess that 1.27 will be just right around there. And I want to know the probability that the standard normal random variable is less than 1.27. Probability is the same thing as area. Now, does less than mean to the left or to the right of 1.27? Less than 1.27 would be to the left, right? Less than to the left. So what I want to find out is all of this area under the curve right here to the left. All right, so since z, or z value, is equal to whatever x we're looking at, because this is a standard normal distribution, then what we can do is just look up in our table z equals 1.27. The way, and so if you've kind of dozed off from my monotone voice, pay attention right now. It's probably the most important thing that I've said so far. The way that these tables work is they will always give you the area cumulative from the left side of the curve all the way up to the z-value that you're at. Okay? So if I look up a z-value of 1.27, it will give me the area from the left all the way up to that value. So table A has negative z-values. Table B has positive z-values. If you look at the little diagram at the top, on either side, A or B, it has a shaded region under the curve. And the shaded region is everything from the far left up to that value. Now, positive z-values are always on the right side. Negative z-values are going to be on the left side, just like a number line. If this is 0, negative numbers are going to be on the left, and positive numbers are going to be on the right. Okay? So if I want to know the probability of this, that our random variable is less than 1.27, if I look up 1.27, so if you look it up, you can go to 1.2, this is in table B, and then the next number, the hundredths, is at the top. So you go to 1.2 and then go over to 0.07. So 1.27. So put your finger on that number, that value there. That is the area under the curve for the x value of 1.27. That's the area cumulative from left to right, or from left all the way up to that number. So what did you get? 0.8980. So all of this area right here is 0.8980. So the probability that the x value is less than 1.27 is equal to 0.8980. All right. So less than will be the area to the left. Less than left. Less than left. And it's good because that's the way that our tables are made. They give you the area cumulative from the far left all the way up to whatever value we're looking at. All right, so let's look at another one of these. So let's compute the area, or let me put probability, because your book likes to use that. The probability that a standard normal random variable is between 0 and 1.27. All right. Your book is not always going to work the problems the same way that I work these problems, because your book likes to teach you how to use tables A and B and C. Every problem that I work, or that we work in here, that relates to this type of data, I'm only going to use table A and B. So if you go to the tutor and that you start looking at the explanations in your homework, they may not be the same way that I show you in class. They may or may not be. But I promise you, if you will just learn one way instead of learning both ways, then it will make more sense. All right, been doing this for 15 years. I've tried to teach people using table C, and it usually confuses them so much that it's not even worth the time. Okay? So I'm going to show you how to do all of this with table A and table B. All right. So first let's draw a picture. So we're going to draw a bell-shaped curve. And you don't have to be perfect, because you can tell my bell-shaped curves are not perfect. All right, we know that right here in the middle that we have 0. And I guesstimated earlier that 1.27 was just, it's one standard deviation plus a little bit more. So it's going to be somewhere around here. So what I'm trying to do is I'm trying to find the area between the two. That will correspond to the probability between the two. Now, our tables are always cumulative from left to right if we use Table A and Table B. Okay. So how do you think we could use the tables to find the area between the two? I know how to find the area all the way up to 1.27, right? I just look at that in the table. I go to the z of 1.27 and I got 0.8980. Well, I want to know this area here. So if I know the area all the way up to that point, what will I need to subtract out to get the area between those two? I'll just need to subtract all of this out, right? If I can subtract all of this stuff out, then I'll have the area between 0 and 1.27. So here's what you always want to do if you're finding the area between two, and these are really z values. If you want to find the area between two z values, here's what you always do. All right? You take the area of the one to furthest to the right. We already know what that is, right? What was that? What was the area of the one furthest to the right? 0.8980 minus the area of the one farthest to the left. All right? Because if we look up 0 in the table, if we look up 0, it's going to give us the area from here all the way to here. It's going to give us all of this. So if we subtract that out, then we'll have the area between the two. So go to your table, go to 0 equals 0.00. You can use either side, but I would probably use B because it's at the very top. And what do you get an area of? 0.5. Just like I told you earlier when I was drawing the bell-shaped curve and showed you the symmetry, if you're at 0, the area to the left is 0.5, the area to the right is 0.5. So we will subtract out the 0.5, and that's my answer. That's the area between the two, which corresponds to the probability. So I believe even I can subtract this, 0.3980. That's my answer. All right, so far, here's the most important things that I've said about using this table. If you want to find the area to the left, you take the value that's in the table. You look up the z-score, and you take that area that's in the table. That will be the area to the left, or less than. So with the less than problems going forward, we're going to find an area to the left when we have a z-score. Okay? If I need to find the area between two values, I'm going to find the area of the one furthest to the right, and I'm going to subtract the area of the one furthest to the left. So in your notes on your PowerPoint, it might be important for you to write something down like it'll be the one furthest to the right minus the one furthest to the left. That's how you find the area between two. All right, so we've done a less than problem. We've done between two value problem. What haven't we done? We haven't done a greater than problem. So if we want to find the area greater than, our tables don't work like that. Our tables only give us the area cumulative to left from left to right. But there's something that we can do to find that value that's not too hard. So let me write down this problem. Let's do and let's use a different value. Yeah, okay. So your PowerPoint uses a different value. It says determine the probability. Anytime you see probability with these, it refers, that's area. That a standard normal random variable is greater than 1.37. All right, let's draw a picture. All right, so let's sketch a bell-shaped curve. Right here in the middle, we know we have 0. With a standard normal distribution, remember the mean equals 0, standard deviation equals 1. So what that does with our z-scores is that makes our z equal to our x value, our random variable. Okay. The problem says, what's the probability that it's greater than 1.37? So if I made 1.27, and this is all guesstimations. I'm not being exact, but if I'm one standard deviation away about right here, then I'm going to draw it pretty much in about the same spot, just a little bit further over. So let's say that that's 1.37. Greater than is going to correspond to the area to the right. All right, so I want you to think about how our tables work and how I could figure out the area to the right there. So what do our tables give us again? They give us the area. If we look this up in the table, if we look at 1.37, it's going to give us the area, all of this from the left all the way to that number. So if I look up in the table, it's going to give us all of this stuff here. So how do you think we can figure out that area to the right? All right, so if I said 1, I know the area under the entire thing is 1, right? So if I say 1 minus the area that I'm given, so the area that I'll be given is all of this that I have purple dots on. If I say 1 minus that area, then I'll get the area to the right. Very good. A lot of you are probably thinking that, you just don't want to say it, but with greater than problems, that's what we'll do. A lot of times we're going to have to use a z formula and calculate the z value, and then we'll find the z value, and then if it's a greater than problem, like this one, I'll say 1 minus, and then look up the area. So look for 1.37, so 1.37, and what'd you get? It's important you can read these tables. More important than reading your phone. 0.9147. All right, so of course I got to do that in a calculator. I can't do that in my head. I probably could, but I'd rather not make a mistake. I've made enough of those today. All right, so 0.0853. All right, and I know all of this, again, it's in the PowerPoint, or it's in the book if you read about it, but I want to try to make this make as much sense as possible. So the area under the curve, under the bell curve, is 1.0. Just like the probability of something occurring that's certain is 1. Right? So we make the relationship of area under a curve relating to probability. Now, if we have a standard normal variable, which most of the times in the real world you're not going to have, you're going to have to standardize the value by using the z-score formula. But if we have a standard normal random variable and we want to know the probability that it's less than, that we get less than that random variable, then less than is to the left. We'll take the value from the table. If we have a problem and it's greater than means to the right, and so we'll say 1 minus the value from the table. If we're looking for a probability between two values, not just 0, like we did 0 and 1.27. It could have been negative 1.3 and 1.3. Then what I would do is I'd find the area of the furthest one on the right, which would be positive 1.3, and I'd say minus, and then I'd find the area of the one furthest to the left, that would be negative 1.3. And then when I find those two areas, say the first one minus the second one, that gives me the area between the two. So that corresponds to the probability. All right. So the type of problems we're going to be working would be like, let's say that I knew that IQ tests had a mean of 100 with a standard deviation of 15. That's like something that's been used for a long time. It changes, but I've heard that used a lot in the real world. The mean of IQ test is 100, standard deviation is 15. All right. I could figure out the probability that a randomly selected person has an IQ score greater than 130. It's not a very big probability. But you can calculate that if you know the standard deviation and you know the mean of an IQ score set. I could figure out the probability that a randomly selected person would have IQ score between 85 and 115. I can actually do that in my head because 85 is 15 points less than 100. So that would be 1 standard deviation to the left. 115 would be 1 standard deviation to the right. The 1 sigma rule tells me that what percentage of values are 1 standard deviation. It's about 68%. So that's what we're doing. We're doing the same stuff that with the 1 sigma rule, 2 sigma rule. It's just that we're not always going to be looking at standard normal random variables. We may be looking at variables that we have to convert over and standardize them. Okay? And that's what we'll go pick up going forward.